You write your program. You hope that when you run it, it works perfectly the first time. Instead, it crashes, red error text fills the side of the screen, and you get flustered. By now, you have built your own habits for this by trial and error, stepping through Python tutor, scattering print statements through the code. Underneath those habits, there is a real strategy, and it starts long before you press run. The material splits cleanly in two. Testing and the validation means you come up with a set of input test cases, and for each one, the output you expect. Then you run the code and check that the expected output matches the output you actually get. Debugging is the other half. One of your tests does not match what you expected, and now you have to work out why. Testing tells you that something is wrong. Debugging tells you what. Each has its own method, so keep them apart. None of that is possible unless the code was written to allow it. The key idea is to write code in a way that makes it easy to test and debug, and the two habits do most of that work. First, write your comments and the specifications as you write the code, not after you have finished it. That helps you now and again when you return to the file days later. Second, modularize. When you notice a chunk of code you are copying and pasting all over the place, pull it out into a small function you call from several places. Habits like these are what defensive programming means. Start with documentation. When you write your own function, fill in the docstring and make it answer 3 questions. What inputs do you expect? What does the function do? What should it return? Here that is spelled out. The input is a non-empty list of numbers. The function computes their arithmetic mean, and it returns that mean as a float. Notice what you get for free. The docstring already tells you what to test and what to expect. The same goes for anything written in a strange way or lifted off Stack Overflow. Comment it. A week from now, you will not remember what that line did. Now the second habit and why it matters. Suppose the same expression appears in 3 different places in your program. One day the rule changes. Names should also have their hyphens removed. So you edit the first copy. You may remember the second. You will probably forget the third. Now your program does 2 different things depending on which path it took, which is exactly the frustration you were trying to avoid. Pull the expression out into one small function instead. There is now exactly one place to change, and every caller gets the change. Break the code into smaller chunks, and each chunk becomes something you can test on its own. The code is written. Testing starts with the easy errors because there is no point reasoning about whether a program is correct while it still refuses to run. A syntax error is caught before your program runs at all. Python will not start it, and it points at the offending line. The other easy kind shows up the moment execution reaches a bad line, an index past the end of a sequence, an operation between 2 types that do not mix, a name that was never defined. One common misconception is worth clearing up here. Where a statically typed language would catch a bad name or mismatched type before running, Python does not. It finds all of these by running. Either way, you're handed the exception name and the line number, which is what makes them the easy ones. Clear them out first. With the errors gone, you write your test cases down before you run anything. Paper and pen works, so does typing them straight into your Python file. For each input, write down the output you expect. The same way test cases are written on the micro quizzes. The point is that the expectation now lives outside your head. When you run the code, you are not trying to remember what the answer should have been. It is already on the page in front of you. Then you fill in what you actually got. Where the 2 columns agree, that case passes. Where they disagree, you have found something, and that disagreement is the trigger for debugging. We are modularizing, which means we are writing functions, and that gives the simplest class of test something small to aim at. A unit test tests a single function with different inputs. You take one particular function, come up with a bunch of different test cases for it, and run them all against that one function. Not one input, many. Ordinary values, the smallest legal input, and whatever edge case you're worried about. If they all pass, that function is done. The narrow scope is the point. A failing unit test has already told you which function the problem is in. Suppose they do not all pass, or you spot a bug while you're still writing the test cases. That is where regression testing comes in, and it is two rules. First, when you find a bug, add a new test case for it. The bug becomes a permanent member of your test set, so it can never quietly come back. Second, when you fix a bug, rerun the code with all of the previous test cases, not just the one that was failing. A fix is an edit, and an edit can break a case that used to pass. Real part running everything is how you find that out. Regression means going backwards. This is the testing that keeps you from going backwards. You go around that loop many times, unit test, regression test, unit test again, until all the modules, all the functions in your program hold up on their own. Then you are ready for integration testing, which takes those modules and puts them together into the larger program. Hangman is exactly this. You wrote a collection of little functions, each doing one individual thing. Is the word fully guessed yet? Show the word with the letters guessed so far. Which letters are still available? Then a big while loop put them together, checking all the different things the user might type and calling the functions you wrote. Every one of those functions passed on its own. The assembled game can still fail, and when it does, you go back and do more unit tests. So the three classes stack, each resting on the one before. Unit tests exercise a single function with many inputs. Regression testing adds a test for every bug you find and reruns every previous test after every fix. Integration testing assembles the modules into the full program and hands you back to unit testing when the whole thing breaks. None of it stands up without the habits underneath, comments and specifications written as you write the code, and repeated code put out into functions. Testing and the validation is comparing what you got against what you expected. Debugging is what you do the moment those two disagree. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.